All right, so yesterday we went over Newton's first law.
This is true.
Okay, and Newton's first law deals with very simple situations in which there is or are no net, there is no net force. Okay, that doesn't mean there aren't forces acting. Lots of times there are. They just all add up to what? 0. Okay, the vector sum of all forces is 0 in any Newton's first law situation. So as a result, Newton's first law deals with all situations where the velocity of the object will not change. Either it stays at rest or just doesn't change velocity at all. Okay, it travels at a constant velocity. There's no math to do with Newton's first law, which is why there's no quiz today. There's nothing really to quiz you on other than what's the definition of inertia, which we don't need to have a quiz for. Okay? Today, we're going to start Newton's second law. Newton's second law will be like 2 weeks worth of stuff because of all the situations that it covers. Okay? There are many, many different applications of Newton's second law. All right? Now, Newton's second law is a mathematical formula. Looks like this. F equals m times a. Now you're probably going, sweet, 2 weeks of a 3-variable formula, that sounds all right to me. Well, it's never quite that simple. Okay? While yes, you're going to use that formula all the time, what you're going to have to remember about Newton's second law is that while F net does equal mass times acceleration, it also equals the vector sum of all forces. So while you have m times a over there, you could have many forces all acting in different directions on the other side of the equal sign. Okay, so there could be, a question where a box, like there's a, a 4-sided tug of war going on a box, and it's being pulled in 4 different directions, and you've got to find out which way the thing accelerates. Well, it becomes a big vector problem at that point. Okay, sure, that all ends up equaling m times a, but it just doesn't end up being as simple as I multiply 2 numbers together. Okay, so that's what we have to look at. There's a ton of different situations where Newton's second law applies. Okay, that's what we'll be looking at. It takes a while to get into all the different types of problems. Today we'll just kind of looking at the simplest ones. Okay, so we got to understand the relationship between force, mass, and acceleration. So again, if we're looking at this formula, F equals m times a, okay, if I increase the force, and this is net force, okay, if I increase the net force, what happens to the acceleration? It increases. Okay, so if I was to just, push this desk a little bit, it doesn't accelerate very much. If I wind up and smoke that desk really hard, its acceleration is quite a bit greater, right? What's changed? The amount of force I exert. Still the same desk, m remains the same. But if I increase force, I'm going to increase the acceleration of the object. Now, if I apply that little force to one desk, not much happens, right? If I apply that same force to a stack of 5 desks, what will the acceleration look like? Bigger or smaller? Smaller, yeah. And now exerting that same force on a much bigger mass, which would result in a much smaller acceleration. Okay, everyone kind of following the idea here? Okay, this is where in lots of different sports, okay, mass becomes an important factor. Okay, you never see like a 5'8", 120-pound offensive lineman in football. Okay, defensive linemen are the guys that protect the quarterback. Okay, they want guys that are really big for that job. They want the 300-pound 6'5" guys for that job. Why? They're harder to move around. Okay, they have way more mass. So all the force you exert on them doesn't result in very much movement. Doesn't result in very much acceleration because of their large mass. Okay, if you put somebody really small and skinny in that position, they're going to get moved around really easily. Same with sumo wrestling. So you never see a small sumo wrestler. Okay, well if you do, they're probably not very good. Okay, because being really big in sumo wrestling is important. I mean, all sumo wrestling is pushing people around. Okay? The bigger you are, the harder you are to push around, the harder you are to push off the mat. Okay? So mass matters in that way. On time, please. Okay, so we got to understand how force and mass influence change in velocity. That's kind of what we were just talking about here, and then obviously solve some problems to do with Newton's second law. All right, so second law deals with what happens when there is a net force acting on an object. If there's a net force, there will be an acceleration. There will be a change in velocity. All right. So when a player strikes a stationary puck, he causes the velocity of the puck to change. All right, so if you've got somebody who's like, waiting to do a one-timer, right? So the puck is sliding along the ice towards them at a constant velocity. Okay, when they strike the puck not only changes direction, but it also speeds up in the direction of the shot. Okay, but that requires a force to be applied. How long in that situation does the puck accelerate for? I'm not looking for like a number here. The acceleration will continue as long as
nothing stops her if it like hits the net or something.
okay, true, yeah, okay, but that would be like once it leaves the stick is I think what you're thinking of, right? But once it leaves the stick, it's also no longer doing what? It's no longer accelerating because what's gone now? The force of the stick. Okay, so that puck will only accelerate as long as the force is acting. Okay, and again, we're assuming perfectly frictionless ice and all that kind of stuff. Okay, so if he hits the puck accelerates as long as the force is being applied. Okay, once the puck leaves the stick, now that force is gone. Now the net force goes back to being 0, and now the puck travels at a constant velocity. In a perfect physical world. Obviously in the real world, once it leaves the stick, it's actually starting to slow down because of friction. Okay? Everyone kind of follow me there? So this is actually where a lot of sports science comes in. Okay? Being able to shoot a puck faster depends on a couple of things. Okay? The force you can exert, which has to do with basically your strength and your technique. Okay? And how long you can exert that force for. Okay? Now your technique would influence the length of time over which you can exert the force, but so does your equipment. Okay? What are hockey sticks made out of these days? Yeah, a number of different materials. They're usually like a composite type of material now that's quite flexible, like kind of graphite and epoxy and things like that. Okay? That are very, very flexible. Okay? Back when I was a kid, a hockey stick was made out of a chunk of tree. Okay? It's just wood, big and heavy. Okay? But wood was a little bit flexible, which made it better than a steel pole. Okay? It was lighter, okay, and a little more flexible than that. But now, with modern sticks, they flex even more. Okay? The advantage of that is a traditional wooden stick might be able to bend just a little. So here's the distance over which a traditional wooden stick would be able to exert a force on the puck because the wooden stick doesn't bend very much. But if you have a composite stick, it flexes a lot, which means now you can exert that force for a longer period of time, which means you are going to shoot the puck faster. Okay? Equipment improvements result in people being able to shoot the puck faster. Okay? Same with golf. Okay, golf clubs, same idea. Okay, if we change the ball, we change the clubs, we change how things flex. The ball sits on the face of the club for longer because it's a little softer now than it used to be. Okay, all of that results in a longer period of time over which the force can be exerted. Okay. Making sense? All right. Okay, so I'll show you what this looks like. Got a shot of it. Okay, so in this unit we have to draw different types of diagrams. You still have to draw vector diagrams, tail to head, especially if you've got like a lot of directional vectors. But first, we need to draw what's called a free body diagram. And that's what you see here. Okay? A free body diagram represents whatever the mass is that's being accelerated okay, with just a box. And then we draw the forces as though they originate from the center of that mass. Okay? So in this case, we've got this box being acted upon by one force that's going to the right and the blue force that's going to the left. Okay? Which way is this box going to accelerate? To the right. The red line is a little bit bigger, okay, than the blue line. All it does is help us to identify what forces are present and what direction they're acting. Okay? It can give us an idea of what's going to happen from a vector perspective. But we would still afterwards want to draw a vector diagram. Probably not for these because they're collinear and it's kind of redundant to draw a vector diagram at this point, but if they were angled, then I would want to draw a vector diagram after the fact. So when we draw a free body diagram, okay, it actually won't be a solid box like this. Okay? A free body diagram will have the mass in the center, whatever it is, 5 kilograms, and then you'll have your forces acting out of it. So let's say a forward force of 20 newtons and an opposing force of 15 newtons, and then maybe you've got these two forces as well, 49.05 newtons and 49.05 newtons. Okay, what's that object going to do? Yeah, it's going to accelerate to the right. Okay, remember, my net force is the vector sum of all the forces that are acting on the object. Okay, there's a force up and there's a force down, but they're the same. So what happens to those two forces? They cancel out. All right, so they're done. Okay, then the only two forces that really matter are the two that aren't balanced. Okay, because when there's an unbalanced force, or net force, there's going to be an acceleration, and that net force is going to be 5 newtons to the right. Okay, now from a vector perspective, if I drew a vector diagram of this, it would look like this. So here's where I start. I would have 49.05, and then I put the next force on the head of that one, because that's how you do a vector diagram. 49.05. Well, look what happened. Those two cancel each other out. All right, but now I'm going to draw the 20 Newton force on the head of the last one, and then I'll draw the 15 Newton force on the head of that one. All right, well, that tells me then that my net force, or my resultant, just like with any vector problem, goes from beginning, right here, to end. 5 newtons to the right. Okay, now, again, would you probably draw a vector diagram for that problem? No. Okay, common sense would be able to tell you what you end up with. But if they're angled, that's what you would have to do. Okay, questions there? So that's how you draw a free body diagram, just like that. Everything is a box. It's great for people like me who can't draw, right? So you don't have to draw, a picture of a person riding a bicycle or a bulldozer, okay, or anything like that. Okay, you just have to draw a box, put the mass in the middle for the box's mass. Okay, this is what we were talking about with the desk versus the pile of desks. Okay, Newton's second law says that your force, your net force, is directly related to your acceleration. Okay? Your acceleration is inversely related to your mass. So in a situation like this, if I have the golfer, okay, and he winds up and hits that ball on the left here, okay, as hard as he can, he's using his maximum amount of force. Okay? The mass of the ball is very small. So it will produce a resultingly large acceleration. Everybody all right with that? Okay? Now, for some reason, he decides a ball is not enough of a challenge, so he steps up to this truck. Okay? And once again, swings his club as hard as possible. Don't try this at home. Okay? The golf course I worked at when I was a teenager and through university, a person did this with a golf cart and ended up dying because they got a piece of the golf club right in the jugular, or actually right in the carotid. Okay? And yeah. What's your natural reaction if you got something stuck in your neck? Oh. Yep. So, keep your cool. Losing a ball is not a big deal. It's certainly not worth dying over. Okay? You don't have to go back and swing your club at the cart. It certainly wasn't the cart's fault or the club's fault. always operator error. Okay?
So maybe
What's that?
he swung at the cart.
He swung out of the cart, and it snapped right in the neck.
Maybe also don't pull something that's in your neck out. 'Cause
Yes,
that's a good way
but
to
you
pull
wouldn't
it.
get to that point if you kept your cool, is what I'm saying. Right?
That's what we-
That was the worst one. That was the worst one I ever saw. The funniest one I ever saw was the guy who put like four balls in the drink, and then in the water hazard. Walked up to the water hazard, threw the bag in, walked up. A little while later, he comes back. I'm like, hi. He's coming back to get his clubs. He just decided, no, I wasn't cool enough. Nope, needed his car keys.
Just done with golf.
Grabbed the car keys, threw the bag further into the water, and walked away.
Done with golf. Never
It's
again.
like, wow, that was an epic quip. Right there. All right, so if he winds up and hits the truck, back on topic, okay, he's now using the same force, but it's on a huge mass. So it's going to produce a correspondingly small acceleration. Okay? Now, if this is the perfect physical world and that truck is sitting on a perfectly frictionless surface, does the truck move? Yes, ever so slightly. Okay? You would have a very small acceleration, but it would only last, that acceleration would only last for as long as the club is exerting the force on the truck. Okay, so there's going to be a very small acceleration, but the truck will slide after that at a constant velocity that would be very, very small, okay, because it's on a frictionless surface. Now, in the real world, does the truck move? Okay, does that mean there's no acceleration? There's still an acceleration. Okay, I may not get the truck as an object to accelerate. But that doesn't mean parts of it don't accelerate. All right? Where he hits it, there will be a dent. Okay? That means that part of the truck moved. Okay? The other part of this is if I'm standing in front of the truck and I have my hand on the truck, do I know when he hits it? Yeah, not only do I hear it, okay, but I also can feel the vibration that impact would produce. That means every single particle that makes up the truck moved. That still counts as an acceleration. I may not have got the whole truck and every particle in it to move in unison and go somewhere, okay? But they all moved, okay? And the vibration would be the evidence of that. Okay? And the dent would be the evidence of that as well. All right, everybody okay with the relationship between force and acceleration and mass and acceleration? Okay, bigger the mass, smaller the acceleration. All right. So when a net force, so this is Newton's second law stated out, okay? So when a net force, F net, acts on an object of certain mass, m, and that's in kilograms, okay? The acceleration that results is directly proportional to the force and inversely proportional to the mass, okay? The direction of the acceleration is the same as that of the force. So whatever the net force is, if it's to the right, that's the direction the acceleration goes. Acceleration and net force always have the same vector because one produces the other. All right, units. The units for force are newtons, but that's an abbreviation. That's kind of paying homage to the guy that came up with all these laws that govern the motion of objects. Okay? It's not actually a newton. When I multiply mass by acceleration, I'm multiplying kilograms by meters per second squared. So a newton is a kilogram meter per second squared when you break it down to its fundamental units. You don't ever have to write kilogram meters per second squared, but know that's what a newton is. Okay, so you can write this force is this many N, okay, for newtons. Just understand that a newton is a kilogram meter per second squared. Okay. And that's just important if, let's say I'm solving for acceleration. I'm dividing newtons by kilograms. Well, that means I'm dividing kilogram meters per second squared by kilograms. The kilograms cancel, and I'm left with meters per second squared. Everybody all right with that? Okay, we'll just know that's what a Newton is. Okay, so free body diagrams, we kind of talked about those already, okay? There's a correct way and a not so correct way to do this, okay? This is the not correct way to do it. Okay? We want to draw our free body diagrams as though the forces act from the center of the mass, okay, or from the object's center of mass. Okay? That's the way we draw them, okay? In this case, we've just got a free body diagram of an object sitting on a table. The force of gravity is pulling it down, the table is pushing up, and they cancel each other, and the box just sits on the table. Okay, everybody all right with the free body diagrams? They're fairly easy to draw. All right, let's look at our first example here. So, two people are pushing a stalled car, because back in the day you could actually start a car by doing this. Okay. How many people can drive a standard? Wow, that's actually a pretty good number because standards have gone the way of the dodo. There aren't many left. The nice thing about a standard is if the battery dies, you just need to get a couple of people to give it a push and you can start it by throwing it in second and popping the clutch after it gets rolling. Okay? In an automatic, that won't work unless you can push it faster than about 30 kilometers an hour, okay? Which would be a neat trick. You basically let it go down the hill. Then you gotta grind it out of park and into that. All right. So with a standard, you can start a car by doing this. So what we've got is we've got a car that has a mass of 1,850 kilograms, and we got two people pushing. One of them pushes with 275 newtons of force. The other one pushes with 395 newtons of force. Okay. Both forces act in the same direction. A third force of 560 newtons, which is the force of friction, is opposing the pushing of the two people. Okay? We want to find the acceleration of the car. All right. What do we need to draw first? Even before that. Free body diagram. Okay? I need to draw a free body diagram of this situation. Right? I don't need anything fancy. I don't have to draw a picture of a car. I just want to write 1,850 kilograms. There's the mass that is being accelerated. Right? Then I want to draw in the forces that are acting on it. So 275 and 395, right? Okay, so those are my two forward forces. Okay, and again, I'm using the same, kind of principles as drawing a vector diagram. My 395 Newton force is longer than my 295 Newton force, okay, or 275. And then I've got the force of friction opposing. All right, that's how you write your givens in Unit 2. You got a Newton's second law question, your free body diagram is your givens. It includes your mass and all the forces that are acting. All right, so now, if I want to calculate the acceleration, I'm going to need the net force, and I already have the mass. Okay, so here's where this goes to. Remember we said F net equals m times a, but it also equals the vector sum of all forces. Okay, your net force is the sum, the vector sum of all the forces acting on the object. If that comes up to 0, what's the car doing? Not moving or moving at a constant velocity. There would be no acceleration if this adds up to 0. right? It's not gonna add up to 0. Okay, so I've gotta find the vector sum of all the forces that are acting here. So I'm gonna say m times a equals 275 plus 395 plus negative 560. I've got one force that's backwards and two forces that are forwards. This will calculate the vector sum of those three forces. And so, sorry, I forgot to start my calculator. Okay, so we've got 275 plus 395 minus 560. All right, so we got 110 newtons as our net force. That equals m times a. Okay, how do I get the acceleration now? Right, divide both sides by m. Okay, so 110 divided by 1,850 kilograms is not going to be much of an acceleration. Right, so it's 0.06 or 0.059. What do we have? 3 significant digits? 0.0595. Okay, so roughly 6 centimeters per second squared. So every second the car is pushed, it will go 6 centimeters per second faster than the second before. That may not seem like much, but if you keep pushing the car, it will eventually add up. All right. Every Newton's second law problem, regardless of how complex it becomes, breaks down to these two things. The vector sum of all forces, which I did here, and m times a. What makes the questions get complicated is the vector sum of all forces part. Okay, figuring out what are all the forces that are involved, what are they doing, which way are they going, okay, that kind of stuff, that's where the questions can become complex. Okay, but otherwise, every single Newton's second law problem will break down to you having to do those two things. Sometimes you'll have to do the m times a first because you'll actually have the acceleration and it'll be asking you what force is missing. So this question could have been worded, the car is accelerating at 0.06 meters per second squared forward and it's being pushed by two people, here's their forces, find the force of friction. Okay, and then I would have to work backwards. I'd find what my net force was, 110, okay, by multiplying m times a, and then I'd figure out what the missing force was. Okay, but they can go either way. Okay, but in the end, it's always going to be those two steps: m times a and vector sum of all forces in every Newton's second law problem. All right, questions on what we did there?
I have a question about the diagram.
Okay.
Would it be wrong if you drew like the two pushing forces into the box and then the other one like the opposite way?
Yes, because that's what I was saying on this slide here. That's not the way to draw it.
Okay.
Yeah? We always want to draw them as though they originate from the center and act outwards.
Okay.
Yeah.
So when you drew on the thing, it was like from the edges of the box. Should we have drawn?
Yeah, I drew them from the edges because I wrote the mass inside and I want to draw over it. So yeah, it's fine to draw them from the edges of the box outwards. Okay. Yeah, it's just saying they originated from the box or from the center of the box. Because as you get more and more forces, obviously you couldn't draw them on top of each other. Right? They'd overlap. Okay, so this is what we just did. They draw I don't like the way they do this because they just draw a point, which we don't like. Okay, draw a box instead, but they did the same stuff we did there. Okay, write this one down, and then we're going to walk through it together. This one involves angle forces. We're not going to change what we do. We're still going to do vector sum of all forces and m times a. I just want to show you one where some of the forces are vectors. So I'll give you a second to get that one written down, then we'll go through. All right, so what they've kind of done here is kind of drawn the free body diagram. I don't really like how they've done it because they didn't write the numbers on any of the arrows, and that's really kind of an important part of your free body diagram. Okay, so the free body diagram for this problem should look something like this. We have a 15 kilogram block. Okay? That 15 kilogram block is being pushed by two forces. Okay? Force 1 is 35 newtons and acts at an angle 60 degrees from the x-axis. Okay? And the second force is 10 newtons and it's along the x-axis. Right? There's my two forces. There's no friction here, okay, so we don't have to worry about that. All right, what do I draw next? So the question wants me to calculate the acceleration of the block. I have the mass. What do I need in order to get A? F net, yeah. Okay, so this is the formula we have to use, right? F net equals m times A. So I need F net. Okay, what's the other way to get net force? The vector sum of all forces. That's the other way, right? So F net equals m times A, but it also equals the vector sum of all forces. Rather than write the whole sentence out, vector sum of all forces. Okay? All right. Well, I can get a vector diagram here and get the vector sum. Would you agree? Okay? Instead of being displacement, it's going to be net force instead, but it's still a vector diagram, just like we would have drawn in the last unit. Okay? So I'm going to have 10 Newton force. Okay, so that line is going to be F net. Okay. Just like the question you had on your unit exam, except instead of displacements, it's forces. Okay, but all vector quantities are added in the same way. We learned that in the first unit. Okay, so let's do the vector stuff then. Okay, if I want to find, if I'm looking at the first vector here, okay, black x is 10 newtons, and that's just positive because it's along the positive x-axis, okay, and y for the black vector is 0 newtons because it's along the x-axis and has no vertical component. Right, for the red one, okay, black x is going to be the cos of 60 degrees, okay, times 35 newtons, which will be 17.5 newtons. And that'll be positive because it's along the positive x-axis. And then red y will be the sine of 60 degrees times 35. That one I can't do in my head. Okay, 30.31. Newtons, and that's also positive because it's up along the positive y-axis. Okay, so now that I have all of that, okay, green x will be 10 plus 17.5, so it'll be 27.5 newtons, and green y is going to be positive 30.31 because there's green y and red y are equal. Everybody all right with that? Vector addition from the last unit. Okay, so now I need to calculate what my net force is. So its magnitude will be Pythagorean theorem, 30.31 squared plus 27.5 squared. Okay, so 40.93. And I'm going to need a vector as well. So theta will be 10 to the minus 1 of the opposite side, which will be y, 30.31, divided by x, which was 27.5. All right, so we're looking at 47.8 degrees. Okay, and that's above the positive x axis. Okay, so now I've got my net force. Am I done? What did the question ask for? Okay, well, accelerate. If F net equals mass times acceleration, then I can calculate the acceleration by taking the net force, which I just calculated, 40.93 newtons at 47.8 degrees, okay, above the x-axis, divided by the mass, which was 15 kilograms. Where was it? Lose it somewhere? 40.93. Where did that number go? I swear I put that number in, didn't I? Okay, well, we'll just do 40.93 because I don't remember what all the decimals were. Okay, divided by 15. All right, so my overall acceleration, I think I only have two significant digits here. Yeah, only two, 35, it only has two. So my overall answer is going to be 2.7 meters per second squared at 48 degrees above the positive x axis. Alright, so that one's a little bit more involved, but still the same two steps. I still did vector sum of all forces, and at the end I did m times a. Right? Everybody okay with that idea? You're probably thinking right now, this gets like more complex. Yep, way more. Okay, but not so much in the math. The math doesn't actually get any harder. It's the visualization of all the forces that could be involved in what they're doing. Okay, there's nothing in this unit that's going to be really mathematically challenging. Okay, probably not even as much as in Unit 1. You're going to have vector stuff. That'll be the most mathematically challenging part of this. Okay, what's challenging is being able to see the situation and go, okay, if it's being pushed this way and being pushed this way, it's going to go this way. Okay, or oh, there's friction involved. That's going to slow it down, and just being able to see all of that. That's the hard part about physics, is visualizing what's going on. All right, any other questions on that one? All right, so I could give you a question like that on a unit exam or a quiz, and then I could have a part B type question.
Would the force two be like drawn second? Since is that
It doesn't matter actually which, I mean, I'll get the same result whether I draw the 10 on the head here or down below, because it's still going to end up going like that, yeah. Okay, all right, so I could ask you a part B. Now that I've, now that we've calculated the acceleration, okay, I could ask something like this. All right, so still the same block. When the force begins acting on the block, it is stationary. What did they just tell me? My initial velocity is? Okay, determine the displacement of the block after 8 seconds. Okay, well, here's the other thing I have to remember. I calculated the acceleration in the last question. It was 2.7 meters, sorry, 2.7. 2.7, yeah. Meters per second squared at 48 degrees above x-axis. Okay, so that's the stuff I have. Can I calculate d? I sure can. Okay. You're still going to be using your acceleration formulas quite a bit in this unit. I mean, if F net equals mass times acceleration, sometimes you're going to have to calculate the acceleration using your acceleration formulas. Okay? So those are still going to be in play for this unit. All right. Since VI is 0, it's just 1/2 times 2.7 times 8 seconds times 8 squared. Okay. Why didn't I use all of the digits? I've told you every time, use all of them, right?
Because you calculated already for significant digits.
Right. It was part of, like if this was a part A and a part B, and you use the answer from part A as a given for part B, you use the rounded value, okay? You can't go back and say, well, suddenly this number is more accurate now because I want to use it in part B. Nope, you calculated it, the significant digits say it's 2 when you start part B. Okay. All right. So we get 86.4 meters is the displacement of the block. But there's only 2 significant digits, so 86 meters along x-axis, positive x-axis. How many people do you suppose, if I put that on an exam, would forget to write along the positive x-axis after their answer? Half, yeah. Yeah, that's a pretty fair estimate actually. Okay, if I gave you a question and you had to do all the stuff you did in part A, calculate the acceleration with all that vector addition stuff, and then I put it in part B, calculate the displacement after 8 seconds, people just get like wiped out and they just forget the simple things, like putting that vector back on there. And actually it's not along the x-axis, it's actually which way, because I'm wrong here. It's right? That was our vector from the first part, wasn't it? 48 degrees above the x-axis. All right. Questions there? That's just an acceleration question, right? All right, let's take 5 minutes. Okay, back 5 minutes and we'll get started on the next one. 5-minute break. Okay, come back here at 1:15. Okay, if you're going out in the hall, remember to be quiet and have your mask up. Okay, let's keep moving on here, guys. All right, I want you guys to copy this one down and give it a try. Okay, it's super easy. Okay, like this is as easy as a Newton's second law problem could ever possibly be. Right. You have a lacrosse player who exerts an average net force of 3 newtons forward on a 0.15 kilogram lacrosse ball while attempting to pass it. Calculate the average horizontal acceleration of the ball during the passing attempt. Okay, give you a few minutes on that one. Okay, how many people think they got it done? All right, so our givens in this one, we're told the net force. That makes it really easy because I don't have to do any vector sum or anything like that. Plus, there's only one force anyway. Okay, and it was 3.0 newtons. Okay, forward. Okay, we were told the mass 0.15 kilograms. We were asked to calculate the acceleration. So F net equals m times a. So acceleration equals F net divided by m. So that's 3.0 divided by 0.15, which should give us 20 meters per second squared forward. Okay, like I said, so that's about as easy as they get. I didn't even draw a free body diagram for that one. Why? There's only one force. What's the point? Okay, I wrote my givens down as F net and M instead of drawing a vector diagram. Didn't need a vector or free body diagram for this one. Okay. Questions on that one? Okay, I want you guys to try those two. Right, so we got a net force. The net force acting on a 6 kilogram grocery cart is 12 newtons to the left. Calculate the acceleration of the cart. The answer's right there. Just go and check yours. Okay, and same thing, answers right here for question number 2. These are both, again, pretty simple questions. All right, so both of these are pretty straightforward. We're given the net force in these, so we don't need a free body diagram. We don't need a vector diagram because they tell us what F net is. Okay, so in question number 1, we know the net force is 12 newtons. We know the mass is 6 kilograms, right? F net equals m times a. So to calculate the acceleration, it's just like the other example we did. F net over m, 12 newtons divided by 6.0 kilograms, okay, gives us obviously 2.0 meters per second squared to the left. Okay, for number 2, we're looking for the mass instead. So again, F net, okay, equals m times a. This time we would divide both sides by a to get the mass. So we would have our net force of 34 newtons divided by our acceleration of 1.8 meters per second squared, which will give us our 19 kilograms there. Questions on those two? Like, you're not going to get many like that. Okay? Those are really, really simple. Like maybe a multiple choice question or something. Okay? It would only be worth 1 mark. All right, try this one. This one's got multiple forces. Okay, so we got 2 athletes on a rowing team or training. One athlete is 65 kilograms. One of them is 70 kilograms. The canoe is 20 kilograms. Okay, athlete A can exert a rowing force of 400 newtons forward, B 420 newtons forward. In the water, there's a resisting force, water resistance, friction, okay, of 380 newtons. What is the acceleration of the canoe? All right, give you a few minutes on that one. What should I do first? Right. Draw a free body diagram. And here's the part that trips people up in this one. What's the mass? It's how much? Okay, 65, 70, and 20. Okay, there's 2 people in the canoe plus the canoe. That's all the mass that's being accelerated, right? Okay, and that's what throws people. They're like 20 because it asked about the canoe. What? The people aren't in the canoe? They're standing beside it and rowing, or what are they doing? Okay, the people are in the canoe. Okay, so we've got our 65 plus 70 plus 20. Okay, so we're 90, 155 kilograms is the mass that's being accelerated here. Okay, the mass of the canoe plus the 2 athletes. Then we're going to have our 2 forces, so 400 newtons and 420 newtons. All right, so that's the force of the 2 people rowing, and then we have a force of drag of 380 newtons. So that would be my first mark on a question like that. Here's my free body diagram with the correct mass. Okay. All right, next thing I got to do is find what? F net. I've got to do the vector sum of all forces. Because in the end here, they want to know what's the acceleration. Well, that's m times a. I've got the mass, but I don't have F net. The only other way to do that is to go 400 plus 420 plus negative 380. All right, so we got 820 minus 380, 460, 440 newtons. Okay, 440 newtons, and that's going to be forward. All right, that number equals m times a. And so now I can calculate the acceleration by dividing both sides by the mass, which we found out was 155 kilograms. Okay, so this canoe is going to be accelerating at 2.84, sorry, meters per second squared, right? We only have two significant figures, so 2.8 meters per second squared. Forward. Forward. There's an R in that word. Forward. Okay. Everybody all right with that one? Now, context of the question is important, right? It's tricky if I don't read things carefully and understand what's going on in the question. I miss important details like the canoe is not empty. Okay? All right. Here's another one. Really important to read it carefully. Okay? You can miss some really important details here because there's a lot of information in this question that is completely useless. Okay? There's a bunch of information in this question that's extraneous. You will not use it to solve the question. It is just there to distract you. So you got to figure out what stuff is important. Trick to this question. What's important, what's not? So in the men's 4-man bobsled event, the maximum mass of a bobsled, 2 riders, a pilot, and a brakeman is 630 kilograms. Am I going to need that number? Nope, completely extraneous. That's the maximum mass. This question is talking about when there are 2 people in the sled and 2 people are pushing. So it won't have a mass of 630 kilograms in the situation involved in this question. Okay, so there's a misleading piece of information. Okay, during a practice run, riders A and B exert average forces of 1,200 and 1,220 newtons each to accelerate a bobsled of mass 225 kilograms, a pilot of mass 98 kilograms, and a brakeman mass 97 kilograms. Okay? Then they jump in for the challenging ride down the blah blah, doesn't matter. Okay? Then it says, during the pushing, the magnitude of the force of friction on the sled, 430 newtons. That's a number I'm going to need. Okay? Calculate the average acceleration of the bobsled. So, first thing, free body diagram. My mass is going to be 225 plus 98 plus 97, which is 420 kilograms. Quite a bit less than 630. Okay, then I got to put my forces on there. 1,200, 1,220, and 430. Now what do we do? Find the net force. 1,200 forward plus 1,220 forward plus 430 backwards, okay, or negative 430. So we're looking at here 2420, 990? 990 newtons. I probably shouldn't do stuff like that, man. Is that the right number? 1990. Yeah, that's better. That's what I should do in my head. Okay, 1990 newtons forward. All right, so now I've got my net force. I used my free body diagram and some vector addition. I didn't have to draw a diagram because they were all collinear. Okay, now I can calculate the acceleration. F net divided by mass. All right, so the 1,990 newtons divided by 420 kilograms, and that should give me my 4.7 meters per second squared forward. Okay, not a mathematically difficult question, and again, that theme is going to be recurring. None of the questions you do are going to be mathematically taxing for you. It's the context of the questions, okay, that can be challenging. Getting the information, getting the right information, and knowing how to use it in the question, that can be the challenging part of these. Okay? Right? The reason we give you questions like this is because it's an important skill for you to develop, to be able to read a question and determine what you need and what's important. The Physics 30 diploma exam often has questions where you will be asked to read a page or a page and a half of text, and then now solve two problems based on your reading. Okay, so reading comprehension becomes a big deal in a question like that. And there's no like tricks, okay? It's not like what's the hidden meaning in this passage or anything like that, okay? But it's what's important out of this passage.
Would we ever have to calculate the weight of like the people pushing the actual object or pulling the object?
I could word it like that. If I had given you the acceleration, right, and all those forces, I could have very easily said, okay, you know, what's the mass being accelerated here? Or if you know that the pilot and the brakeman are this much and the sled's this much, what's the mass of the other two people?
Okay, but in this case, you wouldn't calculate it. It's just like what they're pushing and the weight of like the bus of the two people in it.
Yeah,
Okay.
because they're not part of the mass being accelerated, their mass doesn't play a part. Okay, any other questions on that one? Right. Now, this type of question is very, very common. It's also very simple, okay? But it's a very common type of Newton's second law question. Elevator questions. Okay? There are going to be two forces involved in an elevator question. Gravity and whatever is pulling against gravity. Usually tension. Okay? Tension in a cable that would be used to lift the elevator. Those are going to be our two forces. Any object moving vertically is technically an elevator. Okay? Even if it's like a person jumping out of a plane, it's still an elevator question because they're moving vertically. Okay? So in a question like this, our free body diagram is going to include the force of gravity and an applied force or a tensional force, an upward force of some kind, okay, that's working against gravity. The important thing to realize here is how to calculate the force of gravity. Okay, so we've seen, the only formula that we've really seen so far is this one. F net equals mass times acceleration. Every other force can be calculated in the same way. Okay? Force 1 is mass times acceleration 1. Okay? Whatever acceleration that force would produce, okay? Whatever, that's not the way to say it. Any force is going to produce a certain acceleration by itself if there are no other forces acting. Okay? So all forces are essentially calculated by taking mass times the acceleration they could produce. Everyone okay with that? That's why our formula for the force of gravity is mass times the acceleration due to gravity, which is 9.81, unless you're told it's another planet and then G would be something else. Okay? But for all intents and purposes, it's going to be 9.81 unless you're told otherwise. Okay? So we can calculate the force of gravity by taking mass and multiplying by the acceleration due to gravity. Okay? And we can find any individual force the same way, provided we know what the acceleration is from that force by itself. Okay, so in this particular question, we have a person and an elevator have a combined mass of 600 kilograms. Right? So if we're doing this free body diagram, we would have this here, 600 kilograms. Okay? The elevator cable is exerting a force of 6.5 times 10 to the 3 newtons up. So this force here is 6,500 newtons. I want to find the acceleration of the elevator, well, or person. They're moving together. Okay? The person inside the elevator has to have the same acceleration as the elevator. So, what force am I missing? I mean, if I'm going to find their acceleration, I need to use net force. But in order to get net force, I have to know this force and this force. And this force is gravity, the force that's pulling down on the elevator. Okay. Everybody all right with that idea? Okay. Gravity is always going to be involved in an object moving vertically. It has to be. All right. Can I calculate the force of gravity? Yeah, because I know the mass, 600 kilograms, and I know that G is 9.81. All right, so 5,886 newtons. All All right, which way is this elevator accelerating? Up. Okay, we got 6,500 newtons of force upwards, and we've got 5,886 newtons of gravity downwards. All right, that means that there's more force up. Can I calculate the net force now? Yeah, for sure I can. Okay, my F net will be 6,500 minus 5,886 newtons. All right, so my net force is 114. That's not right. 614 newtons. I must have typed something wrong. Okay, so the net force is 614 newtons up. Can I calculate the acceleration? Yeah. Okay. Now I just divide both sides by mass. Okay, equals acceleration, so 614 over 600, it's just a little over 1. Right, so 1.02, yeah, 1.02 meters per second squared up. Okay, so elevator questions are all basically the same. Gravity acting down and some sort of applied force pulling or pushing upwards, okay, on it. And guys, an elevator question can be as simple as I throw an object vertically into the air. Now, people mess this one up all the time, right? As soon as I say something like, I have a rock in my hand and I throw it up in the air with an applied force of 200 newtons, what does everybody forget? The force of gravity. If I just say, I throw this thing up in the air with this much force, people forget entirely about gravity. They tell me the net force is 200 newtons and they just run with it. Okay? Guys, if there's no gravity, that rock ain't coming back. Okay? And yeah, it's going to have a massive acceleration because there's no force resisting it, apparently. Okay? But there is. There's gravity. Okay? Anytime something is thrown or moved upwards or downwards, gravity is going to be involved. Okay? Don't forget about gravity. Okay? You should never forget about gravity. It's always holding you back. Okay? Always bringing you down. And all the other stupid physics puns about gravity. All right, we'll leave it there for today.